last presentation in this section, titled Automatic Speaker Verification on Compressed Audio by Alexandra Sokol, Georgy Naumenko, Vyacheslav Derkach, Vasil Kuznetsov, Dmitry Progonov, and Volodymyr Gusev, Ukraine. So who will present this paper?
Hello. I would be presenting today. I hope you can hear me.
Yep.
And now you should see my screen, probably.
Yeah, the screen is seen, so the floor is yours.
Okay, thank you. So my name is Alexandra, or Alex for short, and today I will be presenting you to the results of our research on spoofing detection on compressed audio in the automatic speaker verification task. Okay, so first of all, I want to talk about the content of this presentation. In the beginning, I would like to talk a little bit about automatic speaker verification task itself and the current risks that exist in the domain. Then we would discuss existing benchmarks and state of art for mitigating those risks. And afterwards, I will describe our experiments, approach, and results. And finally, we will discuss the real-world case study, our conclusions, and future plans. Okay, so we will start with a quick introduction to automatic speaker verification task as a whole, or domain probably as a whole. And my apologies to everyone who already knew all of that. I'll try to be quick. So automatic speaker verification, or ASV, is a general term describing tasks related to identifying or authenticating users with their voice biometric. ASV and related spoofing subtasks can be divided into two categories: physical access and logical access, where physical access refers to identifying speaker based on speech recorded directly on the microphone and, for example, used in voice assistants. While logical access, on the other hand, refers to identifying audio being recorded and transmitted via some medium. For example, verifying identity during a phone call might be considered a logical access task. From that point on, we will focus our attention on logical access. Okay, so now we need to talk a little bit about voice spoofing. While voice authentication itself is a very convenient way to prove your identity in many cases, it also creates a lot of attack vectors. For example, risks of replay attack when your recorded voice is used to make your voice assistant to do something, or voice deepfakes that may mimic victim's voice during a phone call and may be used for fraud. It's worth pointing out that replay attacks, voice cloning, voice deepfakes, and so on can also fool real people, not only automated systems. The recent events showed that a well-made deepfake, for example, could be used in real-time calls to defraud companies for large sums of money. So how are we mitigating those risks? One option is, of course, to use additional authentication factors, but assuming we cannot or do not want to, the next best bet is the spoofing detection. The idea of most spoofing detection approaches is to create an additional system that would not be used to identify the user per se, but instead would be used to detect if a given audio sample has some inconsistencies in it. An example of it would be liveness detection systems that integrated with voice assistant and used to detect replayed audio. Another example would be some deepfake detection system that might be used to prevent voice cloning fraud during phone calls to a bank or something similar. There exist a lot of publicly available benchmarks for different spoofing scenarios. Probably the most well-known of them is ACV Spoof Challenge, which was started in 2015 and now includes logical access track related to synthesize audio, physical access track about over-the-air replays, and deepfake track, which is similar to logical access but include much more difficult cases. We also must note that there have been a lot of new deepfake-related challenges in recent years. And we can only expect the number of such challenges to increase as deepfakes become a larger risk every day. Current state of art, at least on ASV spoof dataset, can be summarized in the following way. For logical access track, it's possible to achieve error rate as low as 1.3%, while the lowest error on physical access is still as high as 24%. Most solutions in this domain uses inputs from raw audio, spectrogram, MEL spectrogram, linear frequency substral, or constant Q transforms. And at the same time, most common model choices include variational autoencoders, Gaussian mixture models, convolutional networks, most often than not, it's ResNet convolutional networks, and also multilayer perceptrons. So now, why we started our research at all? As I mentioned, one of the novel speaker verification applications is authentication during phone calls. Moreover, to provide secure verification for phone calls, such as bank client identification, it is necessary to understand how cellular and voice over IP networks influence automatic speaker verification spoofing prevention, and then adapt existing solutions to those more challenging conditions. However, a dataset focused on compressed spoofed audio still need to be created. Moreover, there need to be comprehensive research on ASV spoofing prevention that would include various attack vectors, various audio codecs, and transmission methods. I would note that ASV Spoof 2021 challenge do include some compressed and transmitted audio in the evaluation subset. However, full access to the evaluation data, all labels and all description was provided only in October this year, so actually after we already finished our paper. So let's talk about the core idea of this paper. We presented ourselves with the goal of evaluating the performance of existing ASV spoof logical access submissions on compressed audio data, and then adapt those systems to new data and see how much we can decrease the overall error. To make results as general as possible, we selected 8 audio codecs that we used in our experiments. We divided these codecs into 3 groups: older audio codecs used in 2 or 3G networks that tend to have low bitrate and relatively low audio quality; more modern audio codecs used in voice over IP applications that use much more bandwidth but provide much higher quality; and finally, we added a third group with one modern novel generative codec based on neural networks. That last codec should provide mid-quality audio with very, very low bitrate. On the approach, on the model side, we choose to use the deep residual neural network for audio spoofing detection paper and its official GitHub implementation. Represents one of the most common approaches used in ASV spoof challenge, namely using ResNet-like convolutional neural networks to solve the task. And it also can be trained both on MEL frequency coefficients or a log magnitude spectrogram, allowing us to test performance based on various features. Our training approach was based on hard sample mining. So we ran the model on the whole train set, calculated the loss function for all compressed samples. Then we selected only a subset of samples with the highest lost value for each audio codec. And finally, we retrained the model on the selected train subset. Then, of course, we evaluated new model on the whole ASV spoof evaluation subset. In total, we trained 3 models to check how performance would change. First one was trained on 2 and 3G codecs. Second one on 2 and 3G and modern voice over IP codecs. And third one was trained on all codecs that we selected. In the end, we observed following results. First of all, performance on compressed data has from 5 to 12% increase in equal error rate compared to the original. So sometimes it as high as twice as high. With the lowest bitrate older codecs obviously produce the highest error rate. However, applying our approach made it possible to decrease the error rate by 1 to 5% for all the mentioned audio codecs. In the end, the performance of our final model that was trained on all available codecs has much less correlation between bitrate and error rate, and a lower error rate overall. Unfortunately, it also has increased error rate on perfectly clean audio, so 1% increase for MEL coefficients and 4% for spectrogram. Here I presented only the plot for the MEL coefficients, but the results for the spectrogram features is basically the same. However, it would not be a proper research if we stop there, so we evaluated our newly trained models on data transmitted using an actual voice over IP application. To conduct these experiments, we choose to use Discord application. We choose to use Discord for the following reason. First of all, it have rich audio quality settings that would allow us to run same experiment with different audio quality in the future. Second, it's one of the most popular voice over IP services in the recent years. It also uses Opus audio codec that is similar to one used in WhatsApp, Zoom, WebEx, Skype, and other applications. So it's actually quite representative of all other services. And it have unlimited call duration, so it's easy to run experiments overnight or during a weekend. In the end, we replayed a ASV spoof dataset using Discord from one device to another over the course of a few nights. We observed the following results. Base model error rate on the Discord data grow as high as 30 to 35% from the initial 9 to 12%. So basically 3 times as high. However, using the model that we trained earlier on all available codecs, we decreased the error rate to 20% for both MEL features and spectrogram features. Furthermore, while 20% error rate is in no way production-ready solution, it at least shows that it is possible to train on encoded data, and training in the proposed way decrease error rate by about a third, even on the previously unseen data, as we had no Discord transmitted data in the train set. So now let me conclude our results. In this paper, we evaluated error rate increase with various audio codecs, bit rates, and actual voice over IP system. And we proposed and evaluated approaches for reducing error rate on compressed data without a significant increase in dataset size or computational time. Based on the results obtained, we conclude that existing anti-spoofing approaches can be adapted for voice over IP traffic using only limited changes to the training process, such as, for example, training on already compressed data while applying hard sample mining to reduce computational time. Nevertheless, the main limitation of our current work are, first of all, limited amount of data, because we tested only with one dataset, namely ASV spoof, limited number of evaluated models and features, Only one approach for adaptation was evaluated. Only one commercial voice over IP system was tested. And the cellular network was not tested at all. Therefore, we would focus our future work on expanding the number of models and various new datasets, and on testing with an actual cellular network, 2G, 3G, and voice over LTE. Moreover, we also plan to participate in next ASV Spoof 2023 challenge, apply our ideas to newly refined and more difficult dataset, and hopefully to publish our results with code on the GitHub. Thank you all for your time and attention, and please ask any questions. I'll happily answer them. By the way, I also have last appendix page with detailed results for all features and models, but okay. Thank you for attention.
Thank you very much for presentation. And who am I referring to right now, actually? Can you please name yourself?
Oh, I thought I named myself at the start. I'm Alexander Sokol.
Okay, yeah. Sorry. So, Alexandra, yeah, thanks for presentation. I'm very delighted that the guys from Samsung R&D in Ukraine and Kiev also participate in our conference. So, one of my questions will be, can you please, if it's possible, according to the NDA, yeah, understand what's going on here, if it's possible to share the use case for the application which I'm doing this research right now. And the second one will be how can you actually verify by which criteria, or I don't know, by which maybe KPIs, how do you verify the voice? Which criteria do you use for that?
So our main goal for this research was actually not to develop an actual production ready system, so I can talk to you quite openly, probably. And our main idea was related to this scenario that is mentioned on the right side of the slide. So because we saw that, for example, Privatbank in the Ukraine started to provide voice authentication, and some other banks around the world also started doing this in recent years. And because we also saw a lot of deepfake scams and so on and so forth with audio in recent years, we decided that we would like to research this domain, and hopefully at some point it will be some product, so we would have some feature in our phones to present to you. But at the moment, it's mostly the research based on these two use cases. So fraud prevention in bank authentication and deepfake detection in phone calls overall. How we can verify the voice? That's actually a good question. So in our case, we okay, so first of all, I want to return to this point. We did not develop an actual speaker verification system. So we developed a sub-module that should basically detect if the audio is synthesized or not, if it's replayed over the phone, for example, or voice over IP. So we developed this spoofing detection subsystem, not the verification model itself. And what features does it use? It's actually a bit hard to tell you because we used neural networks trained on Mel spectrum or just log magnitude spectrum. So its behavior a bit unpredictable, I would say, in the sense that we can't really point out which features was in use by the model.
Okay, good. Yeah, thank you for your answers. Does anyone have more questions for Alexandra? Okay. Yep, Nikos, please.
So
Just one
sorry,
second.
we had okay. Sorry, we had the wrong microphone muted. So regarding this last answer, sorry, the features used for the spoofing detection model, are they similar to the ones used for the speaker verification model that is accompanying?
I see, I understand. Yes, in this case, it is similar, but that's because of the nature of the data set that we had. Because as I mentioned, we basically, um, in this particular paper, we use ASV spoof dataset, and it's quite hard to get other features from this audio. In the real case, like deployment scenario, if we would collect the data set like totally by ourselves from the scratch, we would actually try to use some additional features. So for example, some information about network condition might be useful. Some information about stereo might be useful because, for example, this particular data set is full mono. So in that particular case, I would even say that features is identical, but ideally we would want to maybe add some additional features if we would collect data set by ourselves.
Understood. But then, would it be possible to merge into one algorithm both decisions? So, the diagram that we saw before with the two branches, it's like you have two decisions for each thing.
Mhm.
One if it recognizes voice, the speaker, and the other one if it's a fake or not. Would it be possible to make the recognition algorithm uh, produce both decisions, so enhance somehow the ASV?
I see, I see. That's a good question. So because at the current moment we use the same features, it is possible. If we would add new features, we would actually would need to see particular like uh, deployment. Like we need to plan for a particular system to see what features we actually can get. Because like we thought about it on the like high level that we would like to use some additional features, but we hadn't started to develop it more deeply for now. Because of that, I'm not sure uh, would it be possible or not. We need to research it more.
It's interesting that there are two decisions for the same problem. So now I see a need to merge to somehow, based on two decisions, create one decision. So it becomes a very interesting problem. Hopefully, you get when proceeding with your research, you get some clever way to combine the two and produce one system that does it both. But it's a very interesting work. Well done.
Yay, thank you. I also want to probably point out that this problem of merging two decisions is I think somewhat solved for the face recognition already, because in face recognition, you, for example, have, face identification itself, basically it would replace the ASV model here that would make a decision about, the person identity. But then you also have anti-spoofing or liveness detection mechanisms present in your on your device. For example, Apple iPhones use infrared sensors of some kind. I don't remember exactly, or something like that. So they, as far as I remember, probably use different features. But for example, Google phones and probably Samsung phones, I'm not sure about it, use the same image for both face identification and liveness detection, basically spoofing prevention, in case of face authentication on mobile devices. So it's, I think it's partly solved in the face recognition. So we would probably try to reuse the same techniques. So.
Yes. Good.
Thank you very much, Alexander, for your answers. Okay, so we are a little bit out of time, as usual. As we finished, it was the last presentation of this section, S2.1, Resilience of Critical Systems. And I thank all the presenters for your brilliant and fruitful presentations, for interesting discussions. And also, I would like to invite everyone presented here to participate in the conference, to attend other sections, and of course, plenary sessions, where the very interesting and prosperous keynote speakers will provide